Good morning, everyone. So thank you very much for the nice introduction. So my name is Anton Klotz, and I'm University Program Manager at Cadence Design Systems, and I'm located in Munich in Germany. So just a couple of words about myself. So I studied in Germany, technical computer sciences, and then 16 years ago I joined Cadence, and I joined Cadence as application engineer. So I was responsible for tape-outs of big digital designs. And then after 11 years, I switched my position and became a university program manager. So just a couple of words about the university program, so what we are doing at Cadence and why we are doing this. So we are interested that students all over the world, they get access to the latest technology, to the latest design tools, so that they can already at university study how to work with these tools. And then when they are finished, so then they can go on a commercial market, and then they can already start designing in commercial environment, but using the same tools, using the same design environment. And this is our aim, that students already have this experience. So if you look at this poster here, so this is briefly what we are offering in the Cadence Academic Network. So this is so we offer access to our support page for the students, so that every student can have access to documentation, to design examples, to training videos. Then we are offering access to generic process design kit. So this is something that you need in order to start using our tools, so that you have some technology which you can already start working on. Then rapid adoption kits. So these are real-life designs, and on these real-life designs, certain design flows or certain tool features are demonstrated. So these are available on our support page, and then you can download them, and then you can use them as a lab and for self-training. We are offering also trainings, so online trainings. So you, as a student, you can be enrolled in these trainings, and then you can accomplish them. So these trainings are about our tools. Lab certification. So this is something that KPI currently has accomplished. So tomorrow there will be an award ceremony that KPI now became a certified university. And we have also a lot of networking opportunities. So since we are Cadence Academic Network, so the network means that we are not only unidirectional, so that we are providing something to universities, and not bidirectional, so that we have some connection with the professor, but we are multi-directional. So that means that also professors who we are in touch with, so they are also recommending other professors so how to use our tools for education and research. And the opportunities for this networking we have at our LinkedIn platform. So, at LinkedIn platform we have certain groups where professors and students can join these groups and then have a discussion there. And also we have an academic track at CDN Live. So CDN Live, this is our user conference. So it's once a year in Munich, so the European one. And there we have an academic track, so you can submit your papers, and then you will get invited. You can present your papers and then also interact with other professors who are also coming to CDN Live. Yeah, so this is just a brief introduction of the university program. So afterwards, I will talk about more detailed about it in a separate lecture. So, but today we are going to talk about history and future of mega trends in EDA. So next slide, please. So, what are the mega trends? So the current mega trends in EDA. First, so EDA stands for Electronic Design Automation. So this is basically describing the ecosystem where Cadence is living. So we are providing software which is used for automatization of electronic design. So we will talk about more or more than Moore. So what it means, so you probably have heard about the Moore's law, so if it's going to continue, or what are the alternatives of it. So then consumer grade to automotive grade. So that means, so currently the majority of microelectronics is for consumer market, but this might change in the future, and then the majority will be produced for automotive market. And what does it mean for the design of microelectronics? Then transistor to system development. So we started with designing single transistors and combining them. But then when we have billions of transistors, so now we have full systems. And so now how to design systems and how to design components for the systems. So then we will talk about cloud. So this is also a mega trend, so that everything what can be moved to the cloud will be moved to the cloud. And so what does it mean for EDA? Then, of course, machine learning is a very big topic. So, and EDA is heavily influenced by this topic. And computing resources are unlimited. So if you move to cloud, so then you have basically unlimited computer resources, but the human resources are not. So this is also one of the reasons why we are doing the university program, why I'm speaking here. So each of these points, so after each point, you will have the possibility to ask questions, because these are quite separate from each other, and therefore it's better that after each point you will have the opportunity to ask questions. Okay, so next slide, please. Okay, so first let's talk about the industry trends. So where does all the microelectronic circuits go into? So this is, of course, mobile. So there are billions of mobile devices which are sold every year, and all of them, they consist of very complex microelectronic circuits. Then social, so all the social networks. So you have microelectronics on the consumer end, so usually via mobile. But then, of course, you have huge cloud installations where all the data which are coming from the end users, they're combined, accumulated, and presented to the other consumers. So then security. So the more data we have, the more valuable they are. So we have to protect them. IoT. So the number of microelectronic circuits which are no longer interacting with human being, but are interacting just between each other, it's always rising. It has already outnumbered the number of devices which are interacting with a human being. Then machine learning, also a very huge topic. So here also the possibilities are not even clear. So what can be achieved with machine learning? So how many operations are possible? Yeah. So big data. So this comes together with social networking. So we have a huge amounts of data which are growing every day, and so we have all to keep them, to storage them, and also to process them. Augmented reality, virtual reality. So this is also a trend which is evolving. So we have always new devices which are enriching our visual perception, and so for virtual reality, they are creating completely new worlds. And so cloud and data centers also comes together with big data and with social networking. Okay, so next slide, please. So the question is now, which of these devices which are described here, especially IoT devices, so they are mostly quite dumb devices. So that means they have a sensor, and then they're transmitting some data into the cloud. And only by transmitting the data into the cloud and by getting some reaction from the cloud, they are suddenly becoming smart. So this is also something that is quite an interesting phenomenon, how to make a system which consists of dumb devices smarter. And this is also quite a challenge for microelectronics. So next slide. So now translate all these trends into the challenges for microelectronics. So the designers of microelectronic circuits, so what do they have to deal with? So this is mixed signal. So that means that more and more circuits, they are combined into one SoC. So SoC stands for System on a Chip. So in the past, we had huge PCB boards with hundreds and thousands of chips on them. And now all these chips, they are merging together. Why? Because it's technologically possible. Therefore, it does reduce costs, and it does reduce energy. So if you have mobile devices, so then everything what reduces energy is helping you to extend the runtime. Then verification. So verification, the more complex the system becomes, the harder is it to verify. So if you make a mistake or you miss a bug in a complex system, so to recreate the system, to fix the bug and then do the tape out and do a final chip, it takes a lot of time, and therefore the more verification you do, the better is it, but the more complex the system is, the more challenging is to do a complete verification and claim that now no bug is present. Then, so PPA stands for power, performance, and area. So these are the three elements which can be optimized in a microelectronic system. So power, so it's the power consumption. Then performance, so how fast is the circuit, and the area. So the smaller a circuit is, the cheaper is it to produce. Then time to market. So as I already said, if you have bugs in your circuit and then you miss time to market, or you have to recreate a circuit, you miss time to market. So then your competitor is faster, and then the competitor gets all the revenue, and you end up with nothing. So you have to start from from scratch. And the IP integration. So currently, no system on a chip is designed by a single company. So usually you are buying some IP blocks. So IP blocks, these are pre-manufactured blocks. So for example, USB or Ethernet. So you buy them from other companies, and then you are integrating them into a whole system. And so now in a modern system on a chip, there are hundreds of IP blocks which are combined into one SoC. But this means, of course, that they all have to be validated, so how they play with each other, and this is also an additional challenge. So next slide, please. So in order to enable that a modern SoC is designed properly and verified properly, so Cadence is investing a lot of resources in order to create all this software, which then we provide to our customers, like for example TowerJazz, and then with our software, all these microelectronic circuits and complete systems are created. So we are continually inventing new products. So for example, in the last 3 years, we have introduced more than 20 products into the market. And a lot of our revenue, we are investing in R&D, because our engineers, this is the most valuable asset that we have, and we always put a lot of revenues into them so that they can continue innovating. So we have filed around 1,800 patents, and we have 26 development centers all around the world. So in Europe, we have at least 6 development centers, plus also centers where support is located, and also sales and marketing. So we have big R&D centers in US, in China, and in India. Okay, next slide. So then a bit history. So Silicon Valley, as you all know, is basically where all the microelectronics started. So in 1955, at Shockley Semiconductors company, the transistor was invented. So then 8 engineers from Shockley Semiconductors, they founded a company called Fairchild. And so if you look who are these engineers, so one of them is Gordon Moore, so who has then introduced the Moore's law. Then Gordon Moore, he went to Intel, so basically he was one of the founders of Intel in 1968. And then from Intel, so the company Zilog was created, then company Xilinx, so which is famous for the FPGAs. And now if we look at Cadence, so in the right bottom, so this is basically a merger between a company called ECAD and a company called SDA Systems. So ECAD, the company was, so they had a product which was called Dracula. So Dracula was a product for design rule checking. And SDA Systems, so this is a company, they had a front-end solution. So front-end solution means that they could do a schematic entry. And then these two companies merged, and then in 1988, Cadence Design Systems was founded. So Jim Solomon, so he was the first CEO. And another very famous name in the EDA business is Alberto San Giovanni Vincentelli. So he's a professor from Italy, and he founded Cadence, but he also founded our biggest competitor, Synopsys. Yeah, so he's still alive. So he is now on our advisory board. Yeah, and so two years ago we celebrated our 30th birthday. So next slide, please. So now let's talk a bit about Gordon Moore and the law which was called after his name. So Gordon Moore, what he said was that the density of transistors is doubling every year. So he claimed this in the 60s, and he had only 4 data points, and then through these data points he just he drew a line, and then he said, well, so in the future this will continue. So he didn't say for how long, and he probably didn't expect that it will take for so long, but yeah, so it became a kind of a self-fulfilling prophecy that his law has to be fulfilled. And you can see there are several statements. So from him every decade basically. So where he became surprised that the law is still valid, but there were some changes. So now the density is doubling not every year, but every 2 years. So in the meantime, it became even slower, but still at a very fast rate. And also, one of the conclusions of this law was that the cost reduction. Actually, the extension of this law was that the density doubles every year, but at the same cost. So this is actually not valid anymore. But he was also saying that the entire cost reduction comes from shrinking feature sizes and growing wafer diameter. So this is also not true anymore. So the cost is actually rising, and this is one of the reasons why people might saying that the Moore's law is no longer valid, because the savings from from shrinking feature and increased wafer diameter are no longer there. But we will look at this more detailed. Yes, and another conclusion is that the cumulative transistors produced increase exponentially with times. So that means that every time when you double the amount of transistors, the cost is decreasing by a fixed percent. And this sentence is actually belongs to a law which is called the learning curve. So the learning curve always says that if you produce something in a large volume, so then the cost of the producing is always decreasing by a certain percent. So therefore, Moore's law is basically an adoption of or a special case of a law which is called learning curve. So next slide. So now that the Moore's law is no longer valid for logic transistors, so because now if we increase the amount of transistors, the costs are not decreasing. But now we can say that Moore's law is continuing to live in memories, because the memories here it's still valid that the more memories you produced, the less cost you have for a certain memory size. And now if we look at a modern SoC, so we see that more than 90% of the content of an SoC is memory. So therefore, the Moore's law is not that important, because the amount of logic is decreasing in a SoC, but the amount of memory is increasing. And for memory, this learning curve is still valid. Okay, next slide. So now you might ask, so if the cost is not decreasing, so why is it still necessary to go further down the geometries? So if you see now the gate cost trend, so this so here you see on the y-axis the cost for a certain amount of transistors in dollars. For a certain geometry, and you see that for 90 nanometers, for 65, for 45, and for 20 nanometers, so the cost decrease was there. But then at 20 nanometers, it basically stopped. And so now you have even slightly cost increase again. So what does it mean? If, for example, if you have a processor and you want to implement a second core on the processor, so when the processor was in 90 nanometers, so then you could include a second core and produce it in 65 nanometers. But then, because of the cost decrease, this second core would come for free. So because of the cost decrease. So this is no longer valid. So that means that in 20 nanometers, so if you want to add a second or a third core, so then the cost of the processor will increase again. But still, it is still so big companies, like for example Apple, they're still going further down the geometries. And why? Because if now you compare to 16 nanometer, the performance gain on the same power consumption is 18% less for 10 nanometer, and for 7 nanometers it's even 35% less. Or if you want to run on the same speed, but you want to reduce the energy consumption. So here you get up to 65 power reduction if you run on the same speed for 7 nanometers. And you can integrate more transistors on the same area. So it will cost you more, but still, if you need additional transistors for additional functionality, you can do it. So this all comes out at a cost. So the design process is getting more and more complicated. So what we have now is so-called multi-patterning. So multi-patterning means that every metal layer you have to produce in 2 steps. So because it's the resolution of the light wave, so which is used for the lithography, is not small enough for this resolution required. So therefore, you need first to do some shapes on metal layer, and then do the other half of the shapes. So then you have huge variations, so local variations. So that means that one transistor might work differently than the other transistors. Then you have a lot of parasitic elements, so for capacity and for resistance. And then you have more DRC rules. So DRC is a design rule check. So you have many more rules than with nodes with bigger geometries. And more corners. So corners, these are conditions, voltage, temperature, and manufacturability condition, which you have to calculate. And so that means that cost of every design is rising. So here we have a statistics that for 28 nanometers, in order to design an SoC, it costs you 30 million, while for 40 nanometer it's 80 million, and for 7 nanometer it costs you $217 million to design an SoC. And this is not stopping, so we are going now to 5 nanometers. So I'm expecting that next processor for iPhone will be in 5 nanometers. And 3 nanometers are already in research, and 2 nanometers, there's a research institute in Belgium called IMEC. So IMEC, they are already working on 2 nanometers, and so here Cadence is also working together with IMEC on a funded project for 2 nanometers. So it goes farther down, but it gets more and more expensive. Okay, next slide. So here, if we look for 7 nanometers, so what kind of challenges do we have with parasitics? So unfortunately, okay, so it works again. So if you see here a structure of a modern transistor, so this is called the FinFET transistor. So you see here's the gate, the green one, and the gray ones, these are so-called fins. So here's so the current is flowing from source to drain via fins. And you can see this is a 3-dimensional structure. So that means that a 3-dimensional structure, you have always capacity parasitics. So you have capacity parasitics from gate to the fin. So then you have capacities from fin to substrate, from gate to substrate. And all these parasitics have to be taken into account for a realistic behavior of the transistor if you want to simulate it. So the number of parasitic elements, so just capacitance, is increasing by magnitude of 6. And then you also have more resistivity, so you have additional layers between the transistor front end and the back end, so these are the metals. So here you have additional layers, so which also have additional parasitic resistivity, so here this is a factor 14. And also for this for the multiple patterning, so there's a new methodology which is called self-aligned double patterning. So which needs new design styles. Okay. So this was about Moore, so how to still continue following the Moore's law, so what challenges we have. And now companies are saying, well, this Moore is too expensive for us, so we cannot afford it, so we cannot buy always new lithography, new steppers, so it's just too expensive. So therefore, another direction, it's called more than Moore. So more than Moore means we can integrate, but we can integrate different circuits into one system. The system does not have to be an SoC. So SoC means that everything is on one wafer, but we can combine several wafers which are produced in several with several manufacturing, and we can combine them into one system. So for example, here we have one substrate, and on this substrate we have a MEMS device, then we have a photodetector, so this is silicon photonics. So here we have an RFIC, so a device for radio frequency, and here we have an SoC and memories on it. So therefore, you have a very fast memory connection through the SoC. So here there's a variety of packaging options. So how you can combine different wafers, so which are produced in different technologies on one substrate, and then just deliver this one substrate to the customer. In this way, you can have a much better integration than before on a PCB. And of course, this comes also with a lot of challenges. So the challenges are here, for example, the heat development. So every device produces some heat, and so that the heat is still not damaging in other devices. So then also a lot of substrate noise, so that if, for example, a digital circuit is creating a lot of noise, that this noise is not propagating through an analog circuit. So this has to be simulated, and it goes even down through mechanical simulation, so that if the device is in some environment where it's shaking, for example, so that the package is still stable enough. And for all of this has to be simulated and verified before the production. Okay, next slide. Okay, so this was about more Moore or more than Moore. So do you have any intermediate questions about this part before I go to the next one? Yes, Victor?
So what you described is mostly about silicon technology, right? Is there any move to other materials?
Yes, so more Moore, it's about silicon. So when we talk about more than Moore, so then of course you can have also gallium arsenide or wafers in different technologies produced and then packaged on one wafer. So when we talk about what comes after silicon, so if we want to integrate even further, so beyond 2 nanometers, maybe 1 nanometer, so here there are some ideas about carbon nanotubes, but this is still research, and so I don't expect it to see before 2025. So at around 2025, we will be at 2 nanometers, and then after 2 nanometers, so here the field is still wide open. So what comes next after this technology? Of course, the question is about quantum computing. So it's also a very, very hot topic. But the question is, what can be calculated with the quantum computing? So if this is not just a specialized accelerator, but the main computation will still happen on silicon. There was a question. Yes, please.
My question is regarding parasitic effects.
Yeah.
When the sockets are integrated on chip or in other place?
Yeah, so I mean it depends on parasitics. So if you see parasitic of a single transistor, so then of course the denser the transistors are together, there are certain parasitic effects because of this dense integration. So you have also some stress in the silicon, so which you have to model. So there's so you will have local variations. Or let's put it this way: when you have a digital design and you have standard cells, and then in the past you could place every standard cell next to the other standard cell, and the standard cells, they did not really interact with each other. So nowadays the placer has to take into account which standard cells can be placed next to each other or not, because of the parasitics, so that a placer must be aware which standard cells can be combined with each other in order to lessen the parasitic effects. So this is for digital. And then if you talk about integration of a system, so here also we have effects from PCB board and also from packaging, which might influence the analog circuit in the chip. And therefore, later I will show that Cadence has developed programs so that you can calculate the parasitics on the PCB, you can calculate parasitics on the package, and then you can count these parasitics in the simulation of the analog circuit and verify if the circuit is still working as it wasn't intended. Yes?
You talked about Apple central processing unit architecture.
Yeah.
But could you explain how ARM big little architecture works?
Big little? Well, it's not part of this presentation. Yeah, basically, I mean, you have one ARM processor, so which is very powerful, and then you have a second one which is less powerful, but it consumes less energy. So that means that if your calculations which are currently necessary, if there's a lot of calculations are necessary, so then the big processor is working and consumes a lot of energy. If less calculations are necessary, so if you are just doing something in the background, so then the smaller processor is working and consumes less energy. So if you are playing a game with a lot of effects, so then the big processor is working. If you just listen to a music MP3, so then the smaller processor is working and consumes less energy. Okay, so then let's go to the next part. So here I'm talking about automotive as the next wave for microelectronic circuits. So so if we look at in the history of the first device with which a regular consumer comes into interaction with microelectronics was a PC. So we started with DOS, or before DOS there was CP/M. So then we had Windows, then Internet came, and this was all done with a regular PC. So then the mobile market started uprising. So then, so first we had 3G. So here we had mostly Nokia devices. Then we have iPhone, Android, LTE. So now 5G is coming up, and so the next wave is expected, or is already coming. This is automotive. So basically, your car becomes a computer or even a supercomputer on wheels. So for car, there are things interesting which are called ADAS. So ADAS is the assisted driving. So these are all kinds of sensors which are measuring what happens on the road, and then translates this information for the driver, or even interacting with the car. So without that, the driver has to interact. So, and then it goes up to completely autonomous driving, so where there's not even a steering wheel, and the car is driving on its own. And of course you might ask, well, so there are billions mobiles on this world, but there are hundreds of millions cars. So basically the quantity is very different. But the amount of electronics which goes into a car is much more valuable than what goes into a smartphone. So basically the manufacturers, they can earn more money with electronics for a car than electronics for the mobile. So here we have a prediction that around 55% of all connected devices in 2020, so basically today, are in the are car related. So if this is true or not, so this is something that we have to calculate at the end of the year, but this was the prediction. Next slide. So why is it necessary to differentiate between consumer electronics and automotive electronics? So here, look at these numbers. So these are completely different requirements. So for example, temperature range. So if your smartphone is in the temperature range between 0 and 40 degree plus Celsius, so this is something that is acceptable. So if you're on a cold winter day and your mobile is not working, well, I mean, it's not good, but it's acceptable. In the car, you have completely different temperature ranges. So it goes from -40 to +165. So you have to optimize your microelectronic circuits to work in this temperature range. So then the lifetime. So mobile phones, usually every 3 years you get a new mobile phone. With the cars, so it's about 10 to 15 years. So you're not throwing your car every 3 years away and get a new one. So usually you want to keep your car a bit longer. So therefore the microelectronics in the car must be more reliable. Then vibration. So it's clear that a car causes more vibrations than a mobile phone. Then ESD safety, acceptable field failures. So you see that the requirements are much more stricter for automotive electronics than for consumer electronics. And this all has to be simulated, modeled, verified, so that it can be integrated into a car. Okay, next slide. Next. Also, a challenge is that usually when a car starts to be planned for production until the first manufactured car, it's usually a 7 year cycle. So if somebody at Audi, for example, wants to bring a new car into the market, he starts to plan 7 years ahead. For microelectronics, so here the product cycle is usually 2 years. So that means that if you start planning with a car and then you integrate electronics, which is already 7 years old when the car is out. So that means that it's not even the last generation, but 2 generations beyond. So therefore, you have to adapt the cycle somehow that when the car is manufactured, so it gets always the latest microelectronics in it integrated. So then, currently, so ECU stands for electronic control unit. So an ECU is basically a chip which is integrated in a car, and then modern cars like Mercedes-Benz has hundreds of different ECUs. So an ECU can, for example, control how you open and close the window. And the idea is to integrate the ECUs, so several ECUs integrate into one. So why it's interesting? Because you are saving costs, since so for 2 reasons. So first, because you don't have to integrate all them on PCB, and you have only one circuit, and then you can use one circuit in more cars. So because if you produce one ECU for every special car model, so then you don't get the mass scaling effect. So if you produce an ECU which is very versatile, which you can use in several cars, so then you save costs. Also, if you integrate ECUs on one system on a chip, so then it's a higher security, it's higher reliability, and also security of supply, so because you just have more chips produced which you can integrate in different cars. So also, if you want to have very advanced features like ADAS, so like assisted driving, so then you have no choice, but you have to integrate it into an SoC because of the amount of data which you cannot transfer on a PCB. So all the data transfer consumption must happen on an integrated chip. Yeah, so Cadence is also involved or wants to be involved in this market. So therefore, what we are offering are IP solutions, so which are called Tensilica. So Tensilica, these are processor cores. So by processor, they are more DSP-like, so digital signal processing cores, which are which can be integrated on an SoC. And these cores, they are specialized on different domains. So for example, we have a DSP core, which is called Tensilica Hi-Fi. So this core is optimized for audio processing. Or we have Vision DSP. So Vision DSP is optimized for vision. So it's optimized for recognizing some objects and processing this information. So a Fusion DSP, it's for sensor fusion. So that means if you have different data, for example, from your camera, from the radar, from LiDAR, so then all this information is then combined in this processor, and then you have an overview about what is happening around you. And finally, the connection connects DSPs are used for radio frequencies. So that means if you have a radar or if you have also Wi-Fi, so there's a new standard which is a Wi-Fi between vehicles where you exchange information between the vehicles. So these kind of processors are used then. So then you use Tensilica connects, and then every core you can combine into an SoC together with other IPs, and then you have an ADAS chip. Yeah, and so just an example for the performance of these DSPs. So there's a benchmark which is recognition of traffic signs. So you have basically thousands of photos of traffic signs in different environments. So when it's dark, when it's foggy, when the sun is shining. And then the benchmark, so then neural network producers are using this benchmark to test how well their neural network system works. And so here we also used our Tensilica processor for recognition of the traffic signs, and we have achieved a very high score. So it's more than 99%. Is there a number somewhere? Okay, I don't have a number, but it's better even than human. So humans have more failure rate than this processor for the traffic sign recognition. So what we simulate. So we have analog simulators, we have digital simulators for the circuits. So what Cadence does not provide is now a cosimulation between a mechanical and electrical. So basically, so for example, just an example, if you have a mechanical model of your brake system, so then basically you press the braking pedal, and then something electrical happens, and then the car is stopping. So this is something that we are not providing. So what we are providing is a pure electrical simulation of a sensor. Then, yeah, this is so currently there are basically two parties which are discussing with each other which approach is better. So one party says, let's place all processing units very close to the sensors, and then they are all working autonomously from each other, and then they process the most amount of information. Only the filtered information is then connected together into a sensor fusion device. While the other party says, well, let's have very, very thick connection to one device, and then this one device is processing everything. so maybe you can even use optical connections to this device in a car. So so it's still a discussion ongoing. So which approach is the right one? So currently I don't have a good answer for that. Yeah. So another issue with the optics. So if you have a crash with your car, so the crash is so the car is not damaged yet, but your optics can break. And if your optical wires break, so then you can basically throw the car away because it's not working anymore. Okay, so the next point is the intelligent system design. So this is currently what Cadence is announcing as its current strategy. So what does mean intelligent system design? It means that so at the beginning, Cadence software was about manipulating single transistors, combining them together, wiring them, then extracting parasitic effects, resimulating, and then out of this circuits are created. So then now we are in an era of several billions transistors in a SoC. So now we are talking about systems, and now when I was explaining about more than more, so we have several chips combined into one system. So now the question is also how to verify that all the systems or all the components are working nicely together. And so here Cadence is offering different products for different levels. So here the core EDA, so these are the software which we were always offering for analog design, for digital design. So then we have package and board. So here we are offering software for PCB design, so which are called Allegro or OrCAD, and for package design. And we have tools for system integration. So these are hardware boxes, which are called Palladium or Protium. So Palladium is based on a custom processor, and with this hardware box, so which is by the way very expensive one, you can simulate the whole system. So you have a Verilog description of the whole system, and then you can load this Verilog into the box, and then emulate the whole system. So Palladium, so Protium is based on FPGA, so you can do basically the same with FPGA. Also, we are offering different IP. So I have already spoken about Tensilica, but we are also offering IP like USB or like Ethernet controller or memory controllers. And we are serving different verticals. So we are serving the mobile vertical, cloud, automotive, aero defense, medical. So basically for every vertical we have a specialized package of our software that we are offering to the manufacturer of these devices. Yeah. Next slide. Yeah, and in the past, the number of parties who were our natural partners was quite small. So we worked very closely with foundries. So from the foundries, we got the technology data. With technology data, we created a PDK, and then this PDK, so PDK is a process design kit, and the PDK we provided then to the customer, and the customer was creating his circuit. And also we worked with IP people. So to IP people, we also provided the PDK. We developed the IP, and then they provided the IP to the customer. So, but now it doesn't work anymore because much more parties are involved. So, next slide. Okay, so next. Yeah. So now we are working also with companies who are producing software for silicon photonics. So this is a company called Lumerical, for example. Also with companies who are producing MEMS. So this is a company called Coventor. With software companies who are writing drivers for the IP, with different standard committees. And also we are working a lot with academia, because we see that a lot of ideas about new systems, they are coming from academia, and also we want to share our knowledge with academia so that they know on which topics the research has the most potential in the future. Yeah, so here there was already a question about how to verify that all the integration of PCB level, of package level, and of the chip does still work, so that there are no parasitics, so which are influencing the performance of the chip. And so here we have also a number of software, so which is integrated together, and then you can extract all the parasitics which are on the board, and then extract all the parasitics which are on package, and then simulate these parasitics together with your chip to see if the specification is still met, and still the chip is working as planned. So here we have, for example, Virtuoso RF. Here. So this is a very new tool which supports the extraction of parasitics on different levels and combining them into one. So then Clarity is a full 3D solver, electromagnetical solver, so that you can simulate 3D structures like they are on PCB, or the connectors from the PCB into the package, and then you have your S parameters, and these extracted S parameters you can use for simulating the whole chip and then the whole system, and then you make sure that the specifications are met. Okay, next slide. Yeah, also you can imagine that if you're combining different chips on a substrate, so then a lot of I/O planning is necessary. So you have to always make sure that all the signals are correctly routed through the substrate, that you have outputs from different tools, from your digital implementation tool, from analog implementation tool, then from the third parties, like from the tool where you develop silicon photonics or MEMS, and then to plan all the I/Os, how they're connected with each other. So here also we have introduced a tool which is called Orbit I/O, and within this tool the chip integrator, so he can plan how all the connections are happening between different chips on a substrate. Also, a special mentioning is about RF signals. So RF is very sensible. So when the RF signals are coming from antenna on a PCB board, then going through the package, going into the chip. So here also a very strict extraction is necessary using full 3D electromagnetic solvers. So Cadence has, as already said, introduced Clarity for a very accurate extraction of the structures on the board and on the package. And so here you have also the full flow from schematic to the layout. Then you do you extract the critical paths in the layouts, put them in a simulation, and then this way you can track your RF signal and make sure that all the signal components are correctly transferred into the processing unit. Okay, so now let's talk about the cloud. So as one of the huge megatrends, so there's a saying that everything what can be moved to cloud will be moved to cloud, and we experienced this at Cadence also. So we have so once we had a IT manager, and he said, well, everything what Cadence is running on systems, we will move to the cloud. So it starts with our web servers, our email server, everything, and this happened. And then last week I heard that he quitted the company because the job is done, everything is moved to the cloud. So now about EDA in the cloud. So so far, companies, they have their own private cloud, or they have a number of servers, and then they run the EDA tools in the on these servers. But the larger the designs become, so then the computational effort is sometimes exponential. So therefore, the number of servers which you have in your own environment is not enough. So you need more processing power, and also when we talk about time to market, so you want to finish all the computations quicker. So therefore, the idea is to move to a public cloud, for example, Amazon public cloud, or Microsoft Azure. And the problem is, of course, there are two major problems. So first is that you have your design locally, and first you have to transfer everything to the cloud. So a design can be several gigabytes in size, so it might take a while until you transfer it to the cloud, and then you can start computing it. Then the other problem is the security. So, I mean, your design is the most precious thing that you have. So this is the whole trade secret of your company. And if this design gets lost, or it gets into wrong hands, so then you basically give away your major competitive advantage. So these are two things which definitely have to be taken into account before you decide to do some computation in the cloud. So therefore, you need special tools which are adapted for these requirements. Next slide, please. So therefore, when Cadence was thinking about developing a new tool for design rule checking, which was specifically designed for running in the cloud, so we have introduced so-called stream processing. So stream processing means that the design is, which we want to verify, is split into so-called streams. And the stream means that this is data which you can upload into the cloud. It's encrypted, so that no one can do anything with the stream if you just have one stream. And you can start computation of the stream before the whole stream is in the cloud. So therefore, you save time during an upload. So you can immediately start. So then another problem is that how to parallelize the algorithm. Because as you all know, in the past it was sufficient to write an algorithm which is working on a single processor. So then, according to Moore's law, the processor gets faster, and then your algorithm gets automatically faster. So then, at some point, processors with several cores appeared. So then you had to think, okay, how can I write my algorithm which scales on several cores? So now in a cloud, you don't have several cores, you have thousands of cores. So now you have to think, how do I write my algorithm which is scaling on thousands of cores? And this is also something which has now been implemented, and it's called the data flow architecture. Yeah, and then so now your algorithms are scaling, and now you have to also control all these cores. So you have to determine which core gets which stream. So how many cores do I have? How many streams do I have to create? How to merge all the results which are processed by the cores into one single result. So this is also something which is not a trivial task, and it has to be created. It has to be implemented. So next slide. Yeah, and the first tool which Cadence has written under assumption that it will run in the cloud, it's called Pegasus verification system. And so now this tool is already usable. So you can download it. You can run it on your designs. And actually, last year, a university in Israel, Bar-Ilan University, so they got access to this tool. So they did a tape out on a 16 nanometer design, and then they wrote a paper about this tool, so how to use it, and then they presented it at our CDN Live. So it was a very nice example of collaboration with the university. So next slide. Yeah, and you can see the results. So the tool which we had before, Pegasus, which was called PVS, Physical Verification System, and PVS was optimized for up to 16 or 32 cores. So it can run locally in a cluster, but it's not suitable for a cloud. And you can see the results. So when we run it on 360 CPUs, so which you hardly have in your company installation, but you have to go to the cloud. So here we had speed ups, so 8-fold, 12, 6-fold, and then we also have near linear results over 1,000 CPUs. So basically, the more CPUs you have available, then it's nearly linear scaling. So the faster you have your DRC results. And usually, so before a tape out, so before the final GDS is going to the foundry, so there's really a time pressure so that all the errors are fixed on your design. So therefore, you want to run DRC as often as possible. And in the cloud, you can do it overnight, while with the old tool, you would need several days or maybe a week till you get the new results. So here we have definitely a productivity increase. Okay, next slide. Yeah, and so you can run Pegasus on your private cloud. So if you're a big, rich company, so like Apple, for example, so you can run it in your private cloud, but you can also run it in a public cloud like Amazon. So therefore, you can save on computing costs, so you don't have to buy servers. You can just run it in Amazon, and it's still secure and it's still fast. No, so I mean, so cloud is basically millions of pretty standard servers, so which are all based on x86 Intel architecture, or so now nowadays Amazon, they have created their own processor which is ARM based, and they put it in their servers, but it has nothing to do with supercomputing, so it's just a huge amount of quite standard servers. Yeah, so I mean, this quantum computing, it's still so very much away from real usage. So you can formulate some problems which can be solved by quantum computing very fast, so faster than with the cloud, for example. But so far these problems are artificial problems, so they are not used in everyday life. So I mean, it remains to be seen. So how real life problems can be mapped on a quantum computing, but so far it's it's still a lot of research to do. Yeah. So I mean, I know that there are universities or companies which are using Cadence software in order to design circuits for quantum computers, but there is no special tool from Cadence so which is supporting design of quantum computers. So there are, I know there are, for example, transistor models so which are adapted for 0 Kelvin. So because usually you need to cool down the quantum computers, so in order to function, so therefore you need a special transistor models to simulate them, and so these models are available. so not directly from Cadence, but from universities and manufacturers. Yeah, but there's no special software for designing quantum computers. I cannot say anything about profitability. So I mean, there are a couple of companies which are developing quantum computers. Yes, so I don't know about how profitable they are or not. Okay, so now let's go through machine learning. So I mean, often machine learning and artificial intelligence they are quite used as synonyms. So which is actually not the case. So artificial intelligence, this is more, let's say, a philosophical term, because it's something which can never be reached as such. So if you look, for example, 15 years back, and somebody tells you, okay, so there is a computer which can understand human speech, and a computer which can show you on the road where you currently are, and which can show you directions, so you would say, okay, this is a very intelligent computer. So nowadays we have Alexa and Siri and Cortana, so no one would really say they are really intelligent. And we have Google Maps, and we say, yeah, well, I mean, yes, we know how it works, but is it really intelligent? No, it's not. So therefore, always when we think of something which is artificial intelligence, so then the computer reached this stage, so then we understand how it works and say, no, it's not intelligent at all. So we understand how it works, but there is no intelligence in it. So this something similar is with machine learning. So what's machine learning? Machine learning is actually a theory about statistics. So it's an application of statistical learning theory, which is well understood already since the 60s. But in the 60s, there were not enough processing power, there were not enough data in order to make this this application really workable. Nowadays, we have the data, we have the processing power, so now we can use machine learning for useful things. Yeah, and so how can machine learning be used in EDA? So EDA is a lot of EDA problems are optimization problems. So you can optimize, for example, what is the optimal routing, or what is the optimal floor planning, or what is the optimal placement, or what is the optimal working condition for a transistor in analog design. So it doesn't have to be the most optimal, but it must meet the specification, so be good enough. And for this optimization problems, so machine learning is a domain which is really can be really used. So there's also not one machine learning specification. There are several different algorithms, so which are working, for example, in a time domain or in a visual domain. So, for example, CNNs, so convolutional neural networks, they are working very well in a visual domain, while RNN, so recurring neural networks, they are working very good for speech recognition. And so there are several other algorithms, so which can be used for different domains in EDA. Yeah, so one example, so where machine learning is already used in EDA is a tool for formal verification. So formal verification means that you try to prove that your design is correct using mathematical proof theorems. Can you please go back once again and once again? So usually there's a circuit, and then there are different ways how to prove it that it's functioning correctly. But the problem is that not every circuit is converging for different algorithm. So that means that you need to find so which Yeah, just leave it like this. So you cannot really find which algorithm is suitable for which circuit. And here machine learning can help. So here in the current version of this tool, Cadence has trained the machine learning algorithm with several designs, and it told that it marked some designs are provable with this algorithm and other designs are provable with this algorithm. And now if you have a new design, so then the machine learning algorithms tries to understand which formal verification algorithm can be used in order to prove the correctness of this design. Yeah, and therefore the tool is now easier to use, because now not the person who is verifying, but the algorithm is choosing the right algorithm, and therefore it's faster to verify. So then next slide. So here the next step is that the system is self-learning. So it doesn't require any additional designs for training, but it tries to identify without training. So which designs can be used, can be proven with which algorithm. So basically, it tries to calculate some designs and then tries to find the right algorithms. So this is then the next version of this tool, which is called Jasper Gold formal verification, and this will be introduced to the market quite soon. What also can be where also machine learning can be applied is for digital design. So as I said, digital design is a lot about optimization problems. So how to optimize power, performance, and area. And so here we have implemented machine learning algorithms in our digital design tools, which is called Innovus. And then when we compare the timing reports of the total output with machine learning and without machine learning, so we see clear advantage with machine learning. So that means that the design is better optimized than without machine learning. And so this tool is already available on the market, and you see here a 12% PPA, so 12% better results with performance, power, and area. And 12% is already quite a lot. So this is you can say this is one technology node, which can be saved just by using machine learning in the digital tools. Okay, next. Yeah, so you can use machine learning for example, for floor planning. So how to optimize the power grid, or for placement, so to avoid congestion, for clock tree synthesis, and also for routing. And when all of this is implemented, so I expect even better results on PPA. Okay. Yeah, and so no, back. Okay, so here, so one thing is to implement just inside. Just leave it as it is. So just to implement the algorithms inside a tool, and the other thing is to implement machine learning in the flow. So basically, a flow, it consists of different design tools, so which are connected with each other, and a good design flow is executing the tools in different order with different parameters. So now the question is if machine learning can optimize the design flow, so it can work on the optimization of the different parameters with which the different tools are started, or can implement a different sequence, how to start the design tools. So this is then the next step of machine learning, so which controls not only a tool, but it controls the whole design flow. Okay, questions about machine learning? Yes?
What sources does artificial intelligence use for learning? Does it learn using open data?
Open?
Open data.
Sorry, I didn't understand. Open? Можно на русском, да.
Какие источники используют искусственный интеллект для обучения? Используют ли он открытые даты?
Открытые даты. Okay, so so there's one problem with EDA. So really, where to get the data for training? So because usually the companies, they are saying, well, the design data, this is something, this is our IP. This is something which we are not giving out to somebody else because we are afraid that we can lose this IP, so it gets stolen. So therefore, it's really a problem. So how to find sufficient data to train a system? So therefore, so Cadence has some design data. So from different error cases, test cases which have been sent to Cadence. Then it's also possible that a company which buys a tool from Cadence, they have their own library of their own data, so which they use for additional training of the tool, so that the tool understands the design style of this company, and then recognizes better the features of a next design. Yeah, so it is definitely a problem. So where to get enough data to train the tools? Yeah. Okay, so then for the last topic, you can do full screen again. Yeah, so now the question is, so we all hear, so as I told you at the beginning of the presentation, there are, it's very expensive to create a new design. So therefore, the number of companies which are moving to the next node is shrinking. So because not all companies can afford to do a design. So what does it mean now for you? So you are studying now microelectronics. So do you have a chance now for getting a job? So after studying, so is it still clever to study microelectronics? So here you see. So what are the predictions of design costs of a modern SoC? And you see that there are more and more domains coming in. So, so at 65 nanometers, so there were very few IP blocks. So it was not a big issue to verify them. So now the IP qualification is already rising. So then the verification amount is rising. The chips are getting complexer, so the amount of verification is complexer. So then the software. So every SoC needs driver, needs a whole ecosystem which has to be written for this SoC. So packaging, okay, validation, prototype. Yeah. So then also packaging is a very big topic. So which is not taught at universities at all. So now it's getting larger and larger. So definitely universities have to start teaching about packaging, about PCBs. So therefore, all these areas need experts, and therefore it's still worth to start studying microelectronics to become expert in these topics. And the additional challenge for microelectronics is that a lot of engineers who are currently working in companies, they are getting old, so they are coming to a retiring age. So therefore, there is now a change of generations. And so you will be then the next generation who will follow up and get experience from these engineers who are going to retire, and then you can replace them and continue innovating for microelectronics. Then as my last slide, so here just an example. So we have an R&D office in Warsaw, in Poland. So here we are currently have open positions for engineers who are developing our IP blocks. So here you see the requirements. So we are designing them in different technologies, so like TSMC, ST, XFAB, Global Foundries, so these are different IP blocks which we are developing, and here we are currently looking for engineers. And this is just one example. So if you go on our website and go into careers, so you will see that there are several dozens of positions opened worldwide for good engineers. Okay, so I think the future for you looks bright. So just study microelectronics, learn how to work with our software. So then how to use TowerJazz technology, and I think the future is bright for you. Okay, thank you.